Okay, before we start talking about chapter 17 and the main topic of it, which is electric potential, I'm going to remind you of something that we saw in chapter 6. So, when we are talking about potential energy, kinetic energy, that chapter about energy. So, suppose we have a particle at a certain height, okay, and we let this particle fall. Okay, so what is happening here? The particle initially, the potential energy, the gravitational potential energy of our particle is initially high, and the final potential energy of this particle becomes lower. Okay, so if I write the final potential energy minus the initial potential energy, I know I'll have a negative value. Okay, so I'm going to write this here. Final potential energy minus the initial gravitational potential energy, some minus something. And I want to complete this equation. Now, why is this object falling? It's falling because of the gravitational force. So this is the gravitational force that is carrying this object down. So this gravitational force is doing work. So the work done by the gravitational force is equal to the gravitational force multiplied by the displacement. So let me call d this height here. Okay, this work done by the gravitational force is a positive value, right? Because the force is in the same direction of the displacement, so this is a positive value. What we saw in chapter 6 was that this change in potential energy, which is a negative value, is equal to minus that work, the work done by the gravitational force. Okay, so in the natural motion of this object, which is to fall, it loses potential energy, and the work done by the gravitational force is positive. So this change in potential energy here is negative. It's a negative value. The work is a positive, gives us a positive value. So this plus with minus gives minus. So everything is clear here. So now let's come to chapter 17. And what we are going to be playing with is we are going to have these two plates, okay, one plate positively charged, the other one negatively charged. And well, things that we know about when we have these two plates, when we are assuming that they are infinite plates. We know that the convention tells us the electric field goes from the positive charge to the negative charge. So this is going to be the direction of the electric field from right to left. And let's now pick a positive charge, and let me carry here on this side where we have the positive plate. Well, this charge doesn't want to be there. Now I have to carry and hold it there, because if I let it go, it will fly away from this positive plate. So what we have is, as I'm holding this particle here, this positive particle close to the positive plate, I can say that this particle has large potential energy. Which kind of potential energy? Electric potential energy. Okay, so initially, making the analogy with what we just talked about, gravitational potential energy, in our case here, we have this positive plate, right? And I'm holding here a positive charge, I'll call it Q, and we can say that this initial potential energy, this initial potential energy of this particle, electric potential energy, is high. If I let it go, this particle will fly away towards the negative plate, right? So once it gets here at this other side, it will have a much lower potential energy, electric potential energy. Okay, what we want to do now is to write the difference in potential energy, the final minus the initial. I know this will be a negative value. Okay, negative value is there. And it's going to be negative of what? Now, what should we put there? Well, we know that it's going to be minus the work. Now, the work done by what? The work that is done by the electric force that is moving this particle to the right. Okay, the separation between these two plates is d. So what I can say is that the change in potential energy is equal to minus the work, which work this electric work caused by the electric force. What is this work? Is the electric force multiplied by the displacement, okay? Which is a positive value. So, as I said, the change in potential energy will be negative. The particle is losing electric potential energy as it moves. The work is positive because the force is along the direction of the displacement. And so positive with negative will give us a negative value. Okay, we could also write this equation in terms of electric field. Remember what we saw in chapter 16, that the electric force is equal to Q multiplied by the electric field. All right? So this Q is the little q that we are putting here between the plates. Okay, so I can also write that the change in electric potential energy, final minus initial, which I know is a negative value because the particle is losing electric potential energy, can be written as equal to minus Q and E. Okay, which is what you see here. Oops, sorry, I forgot to put the D, right? QE is the force, and I forgot to put the D for the displacement, which is what you're seeing here. So what do we have on the right side? Well, the D is the distance, is a positive value. The electric field, what we are putting here is just the magnitude of this electric field, so there is no sign or direction associated with it. It's just the magnitude, and this Q is positive. We are talking about a positive charge. So all this is going to be giving us a positive value, which is the value of the work, and then positive with minus gives us a minus value. Okay, so what I said, positive work with this minus in front give us the minus value, which is the change in potential energy. Very well. What we are going to do now is the same story, but for a negative charge. So you see that up to now we have the problem is analogous to what we have when we are dealing with gravitational force and gravitational potential energy. But when we are dealing with electricity, we don't have only positive charges, we also have negative charges. So how do we describe the same story, now the same game, but now with a negative particle? Okay, again we have our two plates. One is positive, the other one is negatively charged. And now I'm going to bring a negative charge to this game. Okay, on which side will the negative charge have a large potential energy? On the right side. No? So I'm going to start holding my little q, which is negative. Now I'm going to hold it here. So at this point, the particle has a large initial potential energy. Okay, so this is the large, high electric potential energy. If I let it go, if I release this particle, it's going to fly away now towards the positive charge due to this electric force, and it's going to lose potential energy. So once it gets to this plate here, this final potential energy will be low. Okay, so this negative charge moves in the opposite direction of the positive one, of course. Okay, so but I want to write now the same equation, final potential energy minus initial. And this value has to be negative because the particle is losing potential energy. So it's going to be minus something. Minus what? The work. Work, which work? The work done by that electric force. So, and this value of the work, we know it's positive because the force is pointing to the left and the displacement is also to the left. Now the force is in the direction of the displacement, so this work is positive. So then I can also write this as minus the electric force multiplied by the displacement. So here I'm just talking about the magnitude of this force, and here I'm just talking about the magnitude of the displacement. So there are no angles, no directions involved here, just the magnitude of them. Hmm? So this product is positive, but I have this minus sign here, which matches the minus sign for the change in potential energy. So everything up to now is similar to what we had for the positive charge, with the difference that we are now moving to the left, while the positive charge was moving to the right. Okay, now how I'm going to write this in terms of the electric field? Well, the electric field, remember, always goes from positive to negative charge. So this is the direction of the electric field. Okay? Our negative charge is moving opposite to the direction of the electric field. So the work, when we are writing the work, which is positive, the work is, as we said, force multiplied by the displacement. If we want to write it in terms of electric field, now we have to be careful because we are dealing with a negative charge. We have to put this minus sign here. And then the rest is the same, Q, E, D. And why is that? Because of what I said, the particle is moving the opposite direction of the electric field. So we need to worry about this negative charge. But you see, this whole product here will still give us a positive number. Why? It's true that here the E is just the magnitude of the electric field, and this D is just the magnitude of the displacement. But Q, we do care about the sign here, okay? And Q here is a negative charge. So negative with this negative that we put here will give us a positive value. So you see what changes now when we are dealing with a negative charge. Well, we just have to remember that we do care about the sign of the Q. So the change in potential energy is negative. Okay, and how do we write that? I'm going to put minus the work, because the work is positive. And what is the work? The work is this minus QED. So minus with this minus will give me plus QED. But don't worry, because this Q is negative. So I still get correctly that the change in potential energy is negative. Okay, so what changes when we are dealing with a negative charge is we have to remember that the sign of this Q will show up. So we have to correct for that with this minus sign when we are writing things in terms of the electric field. Okay, very well. So that's the end of the first lecture about chapter 17.